Today we are joined by Jack Silva, Teledyne ISCO's application chemist. With that, I would like to welcome Jack.
Hello, thank you for joining our webinar. Today, we will discuss natural products purification. We will discuss the first steps one should take before doing anything. We will do a quick review of chromatography, which will lead into an overview of solvent partitioning. What happens after you extract your compound? We will discuss specialty columns, focus gradients and method development, and how supercritical fluid purification of natural products can help you purify compounds quickly. Natural products are different because we don't know what compounds confer the biological activity. Synthetic chemists have it easy in this respect. They have known products, even if they have side products that give predictable chromatography. In natural products, we start off with a biomass and we don't know what products are in it, and we don't know how to purify it until we've purified it. Before you do anything with your sample, do a literature search. This avoids reinventing the wheel, or you can find your active compound more quickly. Do a journal search. Interesting compounds might be in the Journal of Medicinal Chemistry, for example. This presentation will be posted so you can get the references later. I'll also pause for a couple of seconds so you can take a picture of your screen. Search the family, genus, and species, and this will generate a list of known compounds and existing purification methods. These links were checked very recently, and so they're not dead links as of today, and they contain useful data as of now. Assuming you have your screen shot, I'm going to move ahead now. Do an assay literature search. Companies maintain internal hit lists for different assays, and this is a very useful tool. You might find a given assay tends to show activity with a particular compound class. However, as an example, remember that although CNS assays tend to show alkaloids as active compounds, tetrahydrocannabinol and cannabidiol are central nervous system active, but they are not alkaloids. So if you find that your compound might not be in a particular group, still test it and be sure. We'll have a quick review of chromatography for natural products, which will feed into extraction, and we'll tie it all together later. UHPLC will not be discussed, and we will not discuss the finer details of chromatography, such as solvent modifier or loading technique. We will discuss solvent strength and use this later for correlation to extraction solvents. For natural products, TLC is used, flash, HPLC, and now supercritical fluid chromatography. In this slide, the circles depict the stationary phase. Stationary phase means that it doesn't move, while the mobile phase, as its name implies, does move, and those are our solvents. When the equilibration depicted in the slide is more towards the mobile phase to the right, the compound runs through the column more quickly, and this is caused by stronger solvents, which cause faster elution. Thin layer chromatography is usually silica gel, but alumina, C18, and other bonded phases are used also. TLC can be used to develop C18 methods, but it is often very slow. People generally try to spread out the compounds, but in natural products, we don't know what compound is active or even if it has moved from the origin unless you can do a bioautogram as shown on the left side of the slide. In general, a compound eluting high on a TLC plate will run too fast for a column. It will not give good resolution, and it will not be a pure compound. If you take a look at the bioautogram, number B over there runs a little too quick for good chromatography, while A is a much better choice of solvents. For good results on a column, the compound should be about 1/4 to 1/2 the way up the plate from the origin. So if I used calcium carbonate to purify plant extracts, this is normal phase. We use silica gel for the most part now. Normal phase is the original type of chromatography. The stationary phase is more polar than the mobile phase. Examples that we use now are silica, alumina, sometimes a diol bonded phase. Solvents used include petroleum ether, hexane, cyclohexane, ethyl acetate, acetone, and so forth. I listed these solvents as increasing polarity and therefore increasing solvent strength. Reverse phase is a newer type of column. It is a bonded phase. The mobile phase is more polar than the stationary phase. This means it's reversed from normal phase, hence the name reverse phase. Solvents include water, methanol, acetonitrile, and THF. And again, I'm going from weaker to polar to stronger solvents. Note the polarity order and see how it changes for normal and reverse phase in these two lists. In both cases, the strong solvents are at the bottom. This information is important in determining what solvents to use after extraction. Over here, we have solvent selectivity groups. Solvents in the same group may not help improve purity, but they can be used to affect the retention time based on their solvent strength. Over here, the polarity is in parentheses, and solvents in the same group tend to have similar selectivity. That is the elution order for the compounds. So ethyl acetate is very commonly used. That's in group 6 towards the right side of this triangle. Replacing ethyl acetate with acetone is helpful in some ways, but it won't necessarily improve your chromatography. Solvent partitioning is a very fast cleanup technique. A most common type of solvent partitioning is called cup-chain partition. Cup-chain had many variations of solvents to partition and extraction. We will discuss a version that avoids chlorinated solvent. It is a very good purification technique for screening. It separates compounds by polarity and solubility. And the example we use takes about 1 gram of dried extract, and you dissolve it in methanol and then add 10 mils of water to give you your 9:1 solution. You then partition this with petroleum ether or hexane, 2 times 50 mils, and combine the organic portion, the hexane or pet ether. Do not worry about any suspended solids, as these will dissolve and get partitioned later. Over here, the red arrows suggest some stationary phase and mobile phases that you can use depending on where your activity comes out. So in the upper left, the organic phase, the pet ether, that's very non-polar. And so I would tend to use silica or alumina, and I would use a mobile phase, hexane, ethyl acetate, because those are also non-polar. If I wanted to run reverse phase, I would use something called non-aqueous reverse phase. In the lower right, we have water, and that's very polar, and I would use a technique called Hillock for that, or I would try that. Some people add 1 gram of sodium chloride prior to the THF extraction, which increases the polarity of water. It's essentially the salting out effect. Consider using ammonium chloride instead. This is a volatile salt, and so it will tend to leave your extract as you lyophilize it. Another common partition is one for alkaloids. It takes advantage of the fact that these compounds are basic. This works for most alkaloids. However, test all extracts and phases before discarding anything. If the active compound is an alkaloid, it is possible to purify and identify the active compound very quickly with this procedure. And I will show you an example later in the seminar where I go straight to SFC. Alkaloids with very polar groups may not move very well between the layers. Always verify and check biological activity of all extracts and phases before discarding anything. But essentially, you partition between dichloromethane and aqueous HCl, and the HCl drives the alkaloid into the aqueous layer, which you then collect and add ammonium hydroxide to pH 10, which forces the alkaloid back into the free base, which is soluble in dichloromethane, which is the bottom layer that you then collect. After you extract, the question is, how do you choose a column and solvent? Remember the cup chain partition that we mentioned a few minutes ago? The mobile phase suggestions are from this chart. This is based on a literature review of over 100 references that we did here at Teledyne. Note that this chart is for normal phase, so the stronger solvents are lower in the chart. Use these suggestions for silica and alumina. This chart works because during the extraction, the compounds are very dilute, and it takes a stronger solvent to dissolve the compounds and elute them in a concentrated band off the column. So one thing that you see is that I mentioned if the compound extracted in hexane or heptane, you can run a gradient from hexane to dichloromethane or hexane ethyl acetate, and those are both good choices. Compounds that elute in stronger solvents, such as ethyl acetate, well, you could still do hexane ethyl acetate, but you're roughly in the middle of the orange band. So you run from 30% ethyl acetate to 100% ethyl acetate in hexane, or you can run DCM and methanol. This system works better with a multiple extraction technique, such as a cup chain partition. And the solvent used for extraction is used as the starting solvent in a gradient, the weak solvent. Specialty columns include Cephadex LH20, which is normal phase and size exclusion, CHP20, which is polymeric reverse phase, polyamide, which is generally run as reverse phase, but with phenolic compounds, and ion exchange columns, which are good for alkaloids, phenolics, and acid. So why would you run them on a flash system? Well, first off, you get all of the advantages of a flash system. So you get solvent management, controlled flow, you get a detector and a fraction collector that runs automatically. Solvent management is important for these compounds. For instance, if you let a Cephadex column run dry, it makes cracks and you can't fix them. You can run isocratically. Cephadex swells up differently in different solvents, so you can't really run that as a gradient anyway. The next gen systems can run at a very low flow rate. So Cephadex is really good there. If you run them too fast, the Cephadex compresses, creates high back pressure, and eventually clogs. And like I said, you get a nice detector that lets you combine fractions. Here's an example using Cephadex LH20, and I could combine the fractions due to peak detection. And you see a picture of the setup on the left over here. And then I took the main peak from the previous slide, You can see that it is still a fairly complex mixture. However, I was able to purify two peaks, the epigallocatechin gallate and epicatechin gallate, and they eluted sufficiently pure to give me very good NMR that allowed me to identify them, and flash chromatography was sufficient to finish the purification. Polyamide columns are reverse phase. They go from water to methanol to acetone, and I have 3 gradients over here. And on the next gen 300 systems, you can have multiple solvent inlets, so you can run these chained gradients very easily. This is a very good intermediate purification, and polyamide is very good for phenolic compounds, and it's very good for removing tannins, which cause non-specific binding and false positives in assay. Compared to the Cefidex in the previous slide, it looks like it's simpler. I see different peaks over here. But when I take those different peaks and run them on the HPLC system, I see that they are still complex mixtures. Peaks are resolved, but another purification step would be useful, such as CHP20 or Cefidex. Even so, a great deal of overlap was removed. There's very different selectivity compared to C18 because each C18 run has peaks spanning a wide range of solvent strengths. For example, the major peak in the methanol acetone gradient had polar, that is early eluting compounds in the run. Self-pack columns include strong anion exchange. This column was a quaternary ammonium resin, and I replaced the chloride counter ion with acetate because acetate has a weaker binding than chloride by washing with 1 normal acetic acid before using the column. Weak acids such as phenolics displace chloride very poorly. Compounds captured from ion exchange are greatly enriched due to removal of neutral and basic compounds in the strong anion exchange. You could do a fairly heavy load. This column was 0.5 gram of crude extract to about 15 grams of strong anion exchange resin. And this has to be done as a liquid load so that the compounds are ionized. A strong cation exchange is possible too. I use a sulfonic acid-based SCX resin. I conditioned it with 1 normal sulfuric acid, so I wind up with a proton counter ion in water, and then I washed the column with methanol. Again, I used 0.5 gram of extract for 15 gram of resin, liquid loaded, and I dissolved the mixture in methanol containing acetic acid. This caused any cations to be ionized, and yet the methanol dissolved everything. I ran 2 gradients. The first gradient was acetic acid and water, followed by ammonium hydroxide. This is very useful for enrichment. The neutral and acidic compounds come off during the column wash, and I get the basic compounds coming off in the 2 gradients. Focus gradients allow fast method development. So what we do is we run a scouting gradient, which is a very fast gradient that allows us to see whether the biological activity elutes from a column. So you collect your fractions from a scouting gradient and screen those for biological activity. Then once you know where the compound came off, you can then calculate a scouting gradient to produce a focus gradient. You can use LCMS as well. In this case, I used a 20 by 150 millimeter column, 10 mil fractions, and actually I could have made those fractions smaller for improved resolution on the scouting gradient. And scouting runs and fractions are useful when you can't do a bioautogram, such as assay-directed method development. In this case, my activity was in tube 16 and 17, and I targeted the peak in tube 17. And one thing to note is the scout and prep column must be the same column chemistry. This was run on an AccuPrep HP 150, but you select the area with the biological activity. You use the column to be used for the purification, and the focus button calculates a gradient, and you can scale to a larger column during this calibration. The targeted peak eluded at 6 minutes, and it's a very short run, complete in about 12 minutes, which saves solvent, and yet the shallow gradient maximizes the resolution. SFC is a new technique that can be applied to natural products. The newer systems are very easy to use. It is a normal phase technique, and there are very many columns available for use. As gradients can run from 5 to 70% carbon methanol, there is less chance of the compound remaining on the column, and so you are more likely to be successful with the SFC. SFC is green. It uses non-toxic solvents, so you can use ethanol, methanol, 2-propanol as compared to, say, acetyl nitro for reverse phase. And the carbon dioxide is something every person generates on their own. This is an example of how an alkaloid extraction can quickly jump to a final purification step. Piperine was extracted into dichloromethane, followed by an alkaloid extraction as described earlier. After that extraction, I went straight to SFC and I did a column and solvent screen. Over here, it just shows silica gel, and I eluted it with methanol and 2-propanol. And you can see that the 2-propanol shows much better resolution on the scouting gradient than does the methanol, where all of the peaks are clustered together. I then calculated a gradient to generate a focus gradient on the prep SFC. And then I purified the piperine, and it showed up as a single peak on my analytical. It's a very fast run. The purification was effected in about 3 minutes. So to conclude things, before purification, do a literature search to see what compounds are found in the biomass under study. Extractions are a fast way to resolve inactive compounds from the desired compound. The final extraction solvent correlates with the solvents used on columns, and so you can take advantage of that and purify your compounds more quickly. If needed, specialty columns such as Cephadex and ion exchange can be run with Combi Flash systems. And a new greener option, the AccuPrep SFC, is now available. Thank you very much for your time. And do you have any questions?
Well, thank you, Jack, for sharing your expertise. And as he mentioned, we're now opening this up for any questions that you may have. Please submit them through the Q&A function. I would also like to point out we do have QR codes for our social pages. So if you care to load them, we would love for you to follow us. Thank you, Jack. And with that, I'll turn it over to you to answer the questions.
Okay, our first question is, the recording will be posted in the near future. Wanted to see if the slide deck would be available earlier. If you send us your email, we might be able to make that happen. The next question is about how we determined all of the solvents that we used after extraction, that table on one of the slides. We looked at lots and lots of literature, and what we did was looked at the last solvent the compound was extracted into, and then looked at the first chromatography method used to purify the sample. And then we found a very good correlation between the solvent strength used in the extraction and the solvent strength needed to load and elute off the column. What kind of upper limits are there for the amount of material that can be purified by these processes? With natural products, the initial purification usually only has a very little amount of, well, let me rephrase this. There's only a small amount of compound usually that is active from a given amount of biomass. So the extractions can handle on a gram scale. I think I mentioned 1 gram of sample in about 20 mils of solvent. And you're going to wind up with literally, tens of milligrams of sample afterwards. And as for the chromatography, because the material is fairly crude, the initial purifications also have a very high loading. Again, roughly 10% loading on a normal phase lumina or silica type column, and probably about 5% loading on a reverse phase column. For zwitterion compounds, for example, phenol with amine, what is the best stationary phase? For those, it depends on what it's soluble in. There are some compounds like aminobenzoic acids that run very well in silica gel, for example, and they work rather nicely. But I would try to make one part of the compound neutral. So if I'm running, say, reverse phase, I would use an acidic mobile phase, and that would keep the phenol as the free acid, while the amine is the salt, and I would run it that way with a modifier. Another question I have is on the scouting gradients with the fractions. Why did you say that the fractions were a little too large? I'd like to have the fractions small enough that I can calculate a gradient more easily. The larger the fraction, the bigger the range that the compound could have eluded in. However, it is a trade-off with being able to detect the biological activity, and I felt like 4 or 5 mils would have been better for that example. Another question is going back to the zwitterionic compounds, how would I handle it on normal phase? If I'm running in a non-polar solvent system such as hexane ethyl acetate, or perhaps even DCM methanol up to a point, I might run triethylamine to keep the amine as a free base. And then the phenolic might be acidic. For those of us with a next gen 100, should we do scouting using house-made smaller column? For example, if we have 400 milligrams of reverse phase material, do we run on 1 gram column for scouting and then 50 gram on purification? The problem with the house-made smaller column is you don't know the column volume, and sometime in the near future, we're going to be able to calculate focus gradients from the columns. However, 400 milligram of reverse phase material, do we run on a 1 gram column for scouting and then on a 50 for purification? Well, you certainly can do that. Of course, I presume you're using, say, a solid load cartridge for your gradient or something. But yes, you can do that. We haven't done the calculations for focus gradients on a half a gram column. The other thing to be aware of is that the dwell volume of your system is very, very large, and that's going to affect the scouting gradient greatly. please understand that the reverse phase columns are reusable. So if you use a 5 gram solid, 5 gram column, that might suit you a lot better than the 400 milligram of reverse phase. In addition, the column material is going to be similar between the 5 gram and the 50 gram column. Okay, any other questions, please?